So one of the most important continuous distributions that we're going to work with is the normal distribution. Okay? This is the so-called bell curve. Now, a special case of the normal distribution is called the standard normal distribution. The standard normal distribution is for, say we have a continuous random variable, and if x is distributed as normal 0, 1, then it has a standard normal distribution. This means that the center of the distribution is at 0, and a standardized measure of spread about 0 is equal to 1. As we'll see later on, this is going to be referred to as the standard deviation. The probability curve for the standard normal typically has this special Greek letter phi, and it's equal to 1 over the square root of 2 pi, the exponential function of minus 1/2 x squared, and it's defined for all x between minus infinity and infinity. The cumulative distribution function for the standard normal is represented by the capital Greek letter phi. And so phi of x is the probability that a standard normal random variable is less than or equal to x. It's just the integral of the probability curve from minus infinity up to x. So when we think of this function, it looks like this. It's a nice bell curve. It's centered at 0. And it has this property such that if you look at the area under the standard normal curve, the probability that minus 1 is less than or equal to x is less than 1. This is approximately 2/3. So for a standard normal random variable, the probability that x is between minus 1 and 1 is about 67%. Okay? And then the CDF, again, this integral, we can get the problems. Now, a problem with the normal distribution is that the CDF here doesn't have a closed form solution. So when we integrate this density function, we don't have an analytical antiderivative. So we don't have a closed form mathematical expression for what this integral is. So if we want to calculate areas under the normal curve, then we have to numerically approximate the area under the curve. And software programs like Excel and R have numerical routines that give you very, very, very accurate results for the normal distribution. Okay. So some summaries here. The normal distribution is centered at 0, and it's symmetric about 0. So that means it has the same shape to the left and to the right. And for normal distribution, as I said before, the probability that the random variable is between minus 1 and 1 is, the difference between the CDF at 1 and the CDF at minus 1 is 67%. For standard normal, the probability between minus 2 and 2 is 95%, and the probability between minus 3 and 3 is about 99%. So if you think of, let's see, where are my colors on this thing? Yeah, so we think of the probability curve for the normal. Again, we have minus 1 to 1, and here is 0. And then we have minus 2 to 2, and then minus 3 up to plus 3. And so again, this is about 2/3. And then if you go the blue area, and this is a 0.95, and then the whole area between minus 3 and 3 gives you almost 100% of values. Now, what we're going to see in finance, when we start looking at actual data, say for monthly returns on an investment in like Microsoft stock, we'll find that the empirical distribution, that is when we look at, say, historical data from Yahoo over a 5-year period, we calculate monthly returns every month, and then we, plot the empirical distribution. We sort the returns from largest to smallest, and then we kind of graph what the probability curve looks like. We're going to find remarkably that it looks like a normal distribution. And so this distribution, which is used to describe things like the average heights in a room, IQ scores, things like that, also tends to describe the behavior of asset returns as well, which is a rather remarkable kind of thing. Now, we'll find that the normal distribution may be good in some cases, but not good in others. So, and so that's an important fact that we're going to emphasize throughout the course. One is that the normal distribution is useful. It provides an approximation to the behavior of returns, but it's not perfect. And there are certain features of returns that cannot be captured by the normal distribution. And so when we look at more accurately describing the distribution of returns, we'll be looking at distributions that are different from the normal distribution. And again, that's an important thing to keep in mind as we go forward. Right. Now, because the normal distribution tends to be a pretty good approximation, it's a good model to start with. Right? So we'll be doing a lot of computation and modeling with the normal distribution, because again it works as a rough and ready approximation, and it provides us a workable model in order to do various computations and comparisons with data and so on. So we need to be very comfortable with doing computations with the normal distribution. So for example, we need to be able to find areas under the normal curve. So if you're taking a probability theory with calculus class, you can prove that the integral of the normal probability curve is equal to 1, and you would use the change of variable formula from calculus in order to do this. Now, if you want to find the area between two distinct points under the normal distribution, you have to take the CDF evaluated at B minus the CDF at A, but this can't be done analytically. It's because there's no closed form solution for this. So we have to make use of numerical routines that are in either Microsoft Excel or R or some other program. So in Microsoft Excel, there are actually a number of statistical functions that are available. And in particular, there's a function called normSdist. And this Excel function normSdist computes the CDF for a standard normal distribution. So if you want to calculate the area under the standard normal curve to the left of Z, which would be, then we can use the normSdist function. This normSdist function also allows us to evaluate the height of the normal curve at a particular point. So it gives us the density as well. If we want to compute quantiles associated with the normal distribution function, there's a function called normSinv. So it's the inverse CDF, or the quantile function. So that calculates this quantile. And in R, there are functions for doing computations with the normal distribution as well. So in R, there's a function called pnorm that calculates the probability that x is less than or equal to a given value. Now in R, when you work with distributions, the functions in R for any distribution have all the same terminology. So here, when I want to calculate probabilities from a random variable, you use a function that starts with p, and then there's an abbreviation for the distribution. So pnorm calculates the probabilities under the normal curve. If you want to calculate quantiles, then you use a function that starts with q and then has an abbreviation for the distribution. So qnorm computes the quantile function, which is the inverse of the CDF. And if you want to calculate the height of the normal curve, or the probability density value at a point, use a function that starts with d and then has the abbreviation of the probability model. So dnorm computes the density value of the normal distribution. So to illustrate some of these things, let's just run a few examples of calculating some probabilities under the normal curve. So just to remind you of some particular tricks, so if we have the normal curve, we know that the total area is equal to 100%. So the area under the normal curve from minus infinity to infinity is equal to 1. And if we have some point z here, so the probability that the x is less than or equal to z is this area to the left, but because the total area has to add up to 1, the area to the right of z is 1 minus the area to the left of z, right? So, so that's, yeah. So the probability that x is less than or equal to x is 1 minus the probability, well, I think what I just said was the probability that x is greater than or equal to z is 1 minus the probability that x is less than or equal to z. And the true thing is vice versa. The probability that x is less than or equal to z is equal to 1 minus the probability that x is greater than or equal to z. So if I give you the area to the left, you can find the area to the right. If I give you the area to the right, you can get the area to the left. Now the normal distribution is symmetric. So the probability that x is greater than or equal to z over here is the same as the probability that x is less than minus z. So for a symmetric distribution, so if this is minus z and say this is 0, then the area over here is the same as the area over here. And then because the distribution is symmetric, the area to the left of 0 is the same as the area to the right of 0. So then we can do some calculations. So if you're working in Excel, if you want to find the area, say, of standard normals between -1 and 2, then we just evaluate the CDF at the right endpoint and subtract the CDF at the left endpoint. So we'd use norm S dist evaluated at 2 minus norm S dist evaluated at -1. So that would give us 0.97 minus 0.15. So there's an 81% probability for a standard normal random variable between -1 and 2. If you're doing computations in R, then you would use the p-norm function evaluated at 2 minus the p-norm function evaluated at -1, and you get exactly the same answer. If you wanted to compute quantiles of the distribution, so you wanted to know the 1%, 2.5%, or 5% quantiles, so in Excel, you want to calculate the 1% quantile. We want to evaluate the inverse CDF at probability 0.01. So you'd use the norm S INV function evaluated at this probability, and you see that this is equal to -2.33. So the probability that a standard normal random variable is less than -2.33 is 1%. In R, you would use the Q-norm function because you want to find the quantile. So you say Q-norm of 0.01, and it gives you exactly the same answer. Okay, and then so on and so forth. So those are the simple computations that you would do in Excel and R. When you're working with probability models, say like the normal distribution, I mean, one of the things that you should always do is to, plot the distribution just to see what it looks like. And so, for example, in R, if we want to plot the normal distribution, essentially what we're going to do is we're just going to create a line graph, compute the height of the normal curve at a number of different points. So we know that the standard normal distribution has 99% of its values between -3 and 3. So here I create my x values. So this is the values of x for which I want to plot the normal distribution over. I'm going to create a sequence of values between -4 and 4, and I'm going to take 150 points between -4 and 4. That's going to be my grid of x values. And then what I'm going to do is I'm just going to plot the and the plot command just does an XY plot by default. On the x-axis, I have my x vals, so my values between -4 and 4. And the y values of the plot, I take the dnorm function. So dnorm is the density of the normal evaluated at x-val. So that's just the height of the normal curve. And the type of plot I'm going to make is a line graph. So that's the L option. LWD means line width. When I set that equal to 2, I make the line width twice as thick as the default. So we can see it a little bit better. I specify the color to be blue. And an X label, X lab. So I'm just calling that X. And then the Y label, Y lab is the PDF value. And then, so then I get my graph. So working in R, again, doing something like graphing a density of a distribution is very easy. And these are examples that are done in my book manuscript chapter as well. And you can do similar things in Excel. So if you wanted to plot the normal distribution in Excel, then it would work exactly in the same way. So here I create a grid of x values. I start from -3. Here in this case, instead of going from -4 to 4, I go from -3 to 3. And then to plot the height of the density curve, we use the norm dist function, and it has norm dist is for a general normal distribution, and so this is the B9 is the value that I'm going to plot the normal curve. I set the mean 0, the standard deviation equal to 1, and it has this optional parameter called cumulative. I set that equal to false. This means plot the height of the normal curve instead of the area under the normal curve to the left of a given value. So then I just evaluate this formula and paste it down, and then I can again do an XY plot in Excel by just highlighting essentially these two values and then choosing a line graph, and I can get the probability curve done that way.